The separation logic session, that is, officially. For those of you, if you have empty seats in the middle, could I ask you to move down so that the newcomers can join easily? And if you're sitting near the edge because you think you're going to want to leave early, trust me, you won't. It's an exciting session, and you'll be on the edge of your seat the whole time. Our first speaker, whose slides are not yet being projected. Could we fix that, please? Okay, there we go. Our first speaker is William Mansky, and he will talk to us about an Iris instance for verifying CompCert C programs. Take it away, thank you.
All right, thank you. So as the first speaker in the separation logic session, it's my turn to tell you about Iris. So Iris is a calc-based framework for separation logic proofs. It's very generic, and it's been the target of a lot of work that's really pushed the boundaries of what we can reason about in separation logic. So there's been tons of Iris instances and extensions to the foundations, things like weak memory, distributed systems, and so on. And the way that most of these instances work is that we define a simple core calculus that includes the feature that we're interested in. We define some sort of resource algebra that allows us to model that feature in separation logic. And then we do a bunch of proofs of interesting programs on top of that. There's a smaller number of Iris projects that do something a bit different, that aim to formalize and prove things about code in real programming languages. So there are Iris instances out there for languages like Rust, Go, C, and WebAssembly, with varying details of fidelity or connections to existing semantics and toolchains for those languages. And the work that I'm presenting today adds one more to that list, which is C again, but C as defined by CompCert, the Verified C compiler, with the program logic from the Verified Software Toolchain. So to say a bit about VST, like Iris, it is a calc-based concurrent separation logic verifier. In fact, it's a rather older one than Iris. And it has a lot of the same basic parameters. It is likewise a higher order step-indexed concurrent separation logic, and the way we use it is also very similar in that we have a mix of symbolic execution tactics that run a section of code and show its effect on the separation logic state, and entailment solving that lets us prove that some collection of resources implies some other collection of resources. The big distinguishing thing about VST is that it is mostly specialized to C, and in particular to C as defined by CompCert. And what this gets us at the end is that if we prove something about a C program, then we know that when we compile and run that program, it will actually execute correctly. So what we did in this work was essentially to rebuild VST inside of the Iris framework. So we have exactly the same rules of our program logic, exactly the same adequacy theorem about what we know about programs once they're verified, but the logic that we're using, the resources, the way we're talking about resources and so on, are Iris. And lest this sound easy, this really involved modifying everything. Everything was a bit different from a standard Iris instance from the bottom up, starting all the way from what it means to have a points to assertion in separation logic. So I don't have time to talk about everything that we needed to do to make this work, but I'm going to start from the bottom and give you an idea of why the heap model needed to be different and how we made that work. So one of the key innovations of Iris is this idea that everything is ghost state, even ownership of memory. And the way that works in an ordinary Iris instance is that we have this physical memory, this monolithic map from locations to their values. And then the points to assertion is described as ownership of a fraction of that map. So formally, both of these things are drawn from a resource algebra called the authoritative and fragment algebra, where the authoritative element is a single element that contains the entire memory state, the entire map from locations to values. And then every points to assertion unrolls into ownership of a fragment that just has a single heaplet, a singleton heap that says at this location, we own this share and this value. And this algebra is defined so that if we have these two things starred together in separation logic, if we have the monolithic heap and we have the fragment in a single points to assertion, we can conclude things like if we look up that location in the heap, we will in fact find that value. So all of this works really nicely for building a separation logic on top of this sort of memory. The problem is that it doesn't work with CompCert. because a CompCert memory is not just a map from locations to values. There's a few ways in which it's different, but the biggest one is that CompCert memory also includes permissions. So if we look inside a memory state in CompCert, for each address we'll have some value, which is usually just a byte, but we'll also have some permission drawn from readable, writable, freeable, and non-empty. And the CompCert memory model actually enforces that these permissions restrict the operations you can do. So if you try to, for instance, write to a location that only has readable permission, then the operation will fail, your program will be stuck. And so this causes at least two problems that we need to solve in order to have an iris instance for this model. First of all, that there should be some relationship between the shares that we talk about when we have logical ownership and these permissions that exist in the concrete CompCert memory. And second of all, that CompCert has this permission called non-empty, which isn't readable but also isn't zero. And so we need, in our separation logic, to reflect the fact that it's possible to own a resource but not enough of a resource to actually know what's in it. I'm going to start by explaining how we address the second problem and then get to the first. So the standard iris model of ownership of shares of things is based on the fractional algebra. We have some fraction, some positive fraction, with the basic rule that if we own any fraction at all of a resource, then we know what's inside it. And if we own the full fraction 1, then we can change what's inside it. VST, following CompCert, has a more complicated model of shares. Basically, it models them as a lattice, where we have a bottom share that's no ownership at all. We have an unreadable share, which models this non-empty permission, where we can't know what it is, but we know that it exists, up through readable, writable, and finally the top share, which gives us permission to free a memory location. So the first thing that we needed to do was make a resource algebra in iris that reflects this sort of distinction. In particular, we came up with what we called the algebra of shared values, which has two basic kinds of elements. A yes element, which can only contain a readable share and has some kind of value in it, and a no element, which can only have an unreadable share and doesn't mention the value at all. So if you own a no element, you know that there is a resource there. You even have partial ownership of it, so other people can't get rid of it, but you can't know what the value of that element actually is. And because this is a resource algebra in iris, we define a join operation on these things. It's basically what you'd expect in that if we have two elements joined together, we join their shares. We also join their resources if they have any. And if their shares conflict, so for instance, if we had full ownership in both elements, then we'd go instead to an invalid bottom element. So once we've established this algebra, then we can define our points to connective in terms of it. So when we say L points to V with some share Q, that means we own a fragment of the heap that contains a yes element, assuming that our share Q is actually readable, and then we know what value is in it. And we also define an unreadable points to assertion that's more or less new to VST that says we have a points to here, we own a piece of it, but we can't know what value that is. The next thing is that we need some kind of relationship between these logical elements, these yeses and nos, and the actual values and permissions in the CompCert memory. For this, we define a pretty simple coherence relation that just basically maps each of the shares from that lattice to the corresponding CompCert permission. And then the ownership of memory is defined as, the monolithic ownership of memory is defined as we have some logical heap which is coherent with this CompCert memory. And so taken together, these two things give us a new version of these laws that say, for instance, if we have some CompCert memory M and we also have a points to assertion, then that means we can successfully perform the CompCert load operation on that memory at that location and find that value. So there's a lot more to VST than that. We start with this shared value resource algebra. On top of that, we define our points to assertion and all of the other separation logic assertions we need to talk about pieces of C programs. On top of that, we define verifiable C, the program logic of VST. And on top of that, Floyd, the tactic library that lets users actually prove things about programs. And there's lots of interesting stuff in there. We have our own definition of Hoare triples that's kind of different from the way it's defined in most Iris builds. We have our own adequacy theorem and so on. But just to focus on the top level, at the end, we get exactly the same program logic as in VST, all of the same Hoare triples, and exactly the same adequacy theorem. So when we prove something in this new program logic, same as the old program logic, we know that it runs correctly according to CompCert semantics, and thus will run correctly as compiled code. And this is our big win for this segment. The proofs are almost half the size because we're taking advantage of Iris's nice support for separation logic proofs and its more principled approach in general to proving soundness of separation logic rules. So that's the verifiable C part. Then on top of that, we needed to actually give users a way to prove correctness of programs. And so for this, we re-implemented the Floyd, the tactic library that VST uses. So with the goal that all of the existing VST proofs would still work, and also users would be able to use all of the cool stuff that comes from Iris for free. The Iris proof mode, the fancy ghost state, persistent assertions, everything like that. And the paper has this table listing a bunch of the examples that are present in VST, the C features they exercise, and whether we got them working or not. I'm pleased to report that as of this week, you don't need this table anymore. All of them work. So, to sum up, we've rebuilt VST on top of Iris. It works as before. We can prove all of the same kinds of programs as before. We have the same guarantees about verified programs. And we get for free use of Iris proof mode, fancy ghost state, everything like that. And you can look at the paper for more details on how we define Hoare triples in weakest pre, what the top level correctness assertion for a program is, what the adequacy proof looks like, and so on. What we get out of this ultimately is a verified software toolchain for C that should be a lot easier to maintain. That 43% reduction is going to help a lot easier to extend and add new features to from the whole library of Iris work that's out there. So we're interested in, for instance, in rebuilding refined C on top of VST and getting a semi-automatic verification system for CompCert C. And we're hoping to release sometime in the next few months. You can currently it's on a branch, but we hope to soon have an official release of VST based entirely on Iris and to support that going forward. And I'm also hoping that this work will spur some more interest in the Iris community on doing research on C programs and in general on realistic languages with maybe existing implementations and perhaps even connected to verified compilers. So I'm happy to wrap there and take any questions.
Thank you, William, for being so punctual. In fact, you finished 2 minutes early. Makes my life a lot
My
easier.
pleasure.
So questions for William. Robert back there, and then Peter.
Thank you for the talk. I have 2 questions. One is, I presume that apart from the reduction of the proof size of the Hoare triples, you have also been able to remove all kinds of parts from VST. For example, instead of the indirection theory, you are now using the office from Iris and so on. Is that so?
Right, yes. So I didn't quite diagram it, but we almost had it here. Basically, these 2 lower levels, the one in blue, are completely replacing what VST had there before, the thing we called MSL, I think mechanized separation, I forget what it stood for. And then this verifiable C, that's our mid layer, that's the thing that got smaller, and then the top level of the tactics basically stayed the same size.
So does this mean that MSL has been removed and has been replaced by resource algebras, and indirection theory has been removed and has been replaced by office?
Yes, it means that.
Okay, that's very nice. My second question is, one of the big differences between VST and Iris back in the day was the linear versus affine thing.
Yes.
What happened there?
All right, so you and I have talked about this a lot. We may talk about it more offline.
Also know you changed your mind a couple of times, so I'm
Fair
wondering
enough.
what happens now.
All right, so the current version of this is based on not directly on Iris's base logic, but on the ordered resource algebra framework, which lets us be linear in some resources and affine in others. So we're linear in memory, affine in other things. I'm pretty convinced this isn't necessary, and in some future version we'll just move to the base logic. But for now, it's built on that.
Okay, thank you. I'm, by the way, happy to see a user of the ordered resource algebra thing.
Yeah, it was fun.
Thanks, nice stuff. I'm curious how much of this would change for some other memory object model, leaving aside the CompCert part of the proof?
Yeah, that's an interesting question. It depends. I mean, for CompCert, the fact that it had permissions in the concrete memory was a big deal and something that we need to work around. Another memory object model maybe wouldn't have those, but would have other quirks that we needed to figure out. There's very little that's impossible to model as a resource algebra, so I bet we could do it, but how hard it is would depend on what that object model thought was important to have beyond just map from locations to values.
Yeah, very nice work. Have you put the iris proof mode or any of the new iris features like persistent assertions to work on verifying C programs yet? Or and also have you found it useful? Have you found the iris features complementary to the VST automation?
Yeah, so the place where excuse me, the place where that stuff gets used most heavily is in concurrency. I don't have anything to say about concurrency with this system yet because the concurrent soundness for VST is already hugely complicated. But we definitely have some examples where it's really nice to have the iris proof mode. Just, we were rewriting with associativity and commutativity before, and now we can just say, get this hypothesis, frame it. And there's also persistency for things like function pointers is very convenient immediately.
One question over there.
I'm wondering, if I understood correctly, in VST you had a model that was based on a lattice, right, without fractional permissions, and then in Iris you go into PCM with fractional permissions. So one question is, if I understand correctly, wasn't there a more direct mapping? And the second question would be, are you making use of those fractional permissions?
Right, so to be completely clear, for memory, we do not use fractional permissions. We can't use fractional permissions because there's this idea of unreadable but non-zero ownership. In practice, what we're actually using is tree shares, but it doesn't really matter. It just has to be any share that meets this lattice, and that's what ownership of memory is built on. We don't take advantage of fractions at all for that.
Okay, thank you.
There's a question back there.
Thanks. Is there a chance of porting to transfinite iris and getting a total correctness logic for C?
I think there is a chance. I do not yet know how complicated it would be. I tried for this to do later credits, which I think is simpler than that, and ran into all sorts of problems because our semantics and our WP don't have the same shape as a standard iris instance. So it would probably be non-trivial, but I'm sure it's possible.
Okay, thanks.
Any other questions for William? Oh, there's one here. Maya.
You had a table with the verified C programs. I was wondering how much proof effort it was to verify all of those, and if you have automation support for any of these proofs.
Yeah, I mean, I have, I guess, I didn't write VST lines of code here, but all of these were already verified in VST, so I can't give you a good measure of the proof effort right now. It was not very much proof effort. We have a sort of compatibility file you can implement in old VST proofs usually just work. So it wasn't very much effort to port them once we had all the tactics working, and of course it was a huge amount of effort to make the tactics work. But the automation level is VST standard automation level, which basically is like Iris's standard mode. You have one symbolic execution tactic per command in the program.
Okay, let's thank William again. Thank you.